Welcome to this video in the rates 2 topic. The aim of this is to look at how you can determine reaction orders, how you can deduce these orders by the behavior of consecutive half-lives in a concentration time plot. So let's start with first order reactions here. So remember, the definition of the half-life was the time it takes for the reactant concentration to half. So if we think about at the start of this reaction, its concentration is 1. Then after a single half-life, then its concentration should be 0.5. So if we show that on here, it's gone down to 0.5. It's taken about 14 seconds in order to do so. Okay, what would the second half-life be? Well, it's half of this, so it's going to go down to 0.25. So the second half-life, to get down to there, it's going to go to about 28 seconds, and the third half-life to get down to 0.125 is now taking about 42 seconds. And so if we look on the graph here, and we can just mark the half-lives on, then the first half-life here is 14. The second half-life, to get another halving of the concentration, is also 14, and the third half-life is a further 14 seconds. So to get from there to there, we've got to go up by 14. From there to there is 14. From there to there is 14. So what we've got here is a constant half-life. So for a first order reaction, we've got constant half-life. And it's really important that if you're going to prove that something's first order, then you've got to use 3 consecutive half-lives. So constant half-life for a first order reaction. Let's look at second order reaction. Now try and bear that shape of the first order reaction in mind. This is a concentration time plot for second order, and it's much steeper at this point here. Let me just highlight that for you. So if we look at the initial rate of reaction here, that tangent right at the beginning, compare that to the first order reaction, it's much steeper for a second order reaction, and that's just because we've got here rate equals K times reactant concentration squared, and therefore when reactant concentration is very high, then the rate is going to be very fast, whereas when we get down to the bottom here, when reactant concentration is very low, then we've got a much slower reaction because it depends on the square of the concentration. Anyway, back to thinking about half-lives. So when we think about this reaction here, let's see what happens. So the first half-life down to 0.5 from 1, we measure that there, that looks like that is around about 5, so 5 there. Do our second half-life, it looks as if we're going to be around about 15 maybe at that point. And the third half-life going down to 0.125, it's going to take us all the way up to around about, say, 34 there. So in this case, when we look at it, our first half-life here is only 5 seconds. Our second half-life here is 10. And our third half-life here is a whopping 19 seconds. And so what we've got here is an increasing half-life. Again, we've used 3 consecutive half-lives to show this. Increasing half-life over time. So we can use that essentially as a hallmark. So if we had a constant half-life, as in the case of first order reaction, then we would deduce first order. If we have an increasing half-life over time, we've got a second order reaction. Let's go to what a zeroth order reaction would be like. Again, we do exactly the same thing. So first half-life down to 0.5, that's taking around about 25 seconds to happen. So that first half-life here, 25. The second one down to 30, it's around about 38 there perhaps. So that second half-life has only taken about 13 seconds. And then to go down again from 0.25 to 0.125, that's probably about 43. It's only taken there around about 5 seconds to happen, so it's 43. And so what we've got happening here is a decreasing half-life over time. Now, if you were presented with this reactant concentration against time graph that's a straight line, you should immediately be thinking, well, that's a zeroth order reaction. But this relationship will help to concretize it. So, in summary, imagine we've got three reactions here. Zeroth order reaction, reactant concentration goes down, constant rate with time, and then just flat lines. Now, in this case here, the half-lives of the reaction, so if you go down to half, another half, another half, so the half-lives here so the half-life t half is decreasing. If we take a first order reaction, then we've got reactant concentration just going down relatively gently with time. And if we take this reaction here, in order to go down to half, we're going to go to about there, half again, it's about there, half a third time I can't draw on, but here we've got a constant half-life, so T half constant, and in a second order reaction we've got a much steeper graph at the beginning which then levels out much more sharply, something like that. And in this case here, the first half-life is about there, is much the shortest, and then by the time we get to the third half-life, so here, that one's quite a bit longer, and this one's longer again. So we've got T half increasing over time. So we can use this to distinguish between zeroth, first and second order reactions, and just to underscore this, must show this is most commonly used for first and second order, but we must show this with three consecutive half-lives, just like I've done in all the examples in this case.